Well, good afternoon, cohort B, my second favorite cohort. Guys, how are you doing? I hope you're doing well. Okay, so I've got a lesson for you here today and a couple of worksheets, and we're going to finish electricity today. And then we've got just one unit left after that, but we'll talk about review and everything when I see you tomorrow for the test for electricity. But let's, before we get into anything like that, let's finish this off, okay? So by the way, I've been posting answers here. I posted some of the answers to the Kirchhoff law worksheets that we worked on here yesterday. I didn't put all the answers in yet, but I will, okay? And by the way, some of you were asking on the group chat about number 5 and 6. You can do those. You can use, I'll just put it here, you can use the DC, the FET DC circuit builder to test this yourself, okay? All right then, now that we've gone over that part, I just want to show you where we are in the electricity outline before we get started. So we've done everything. I told you not to do the textbook homework. I'm giving you worksheets instead. So we have now done this. We did that as well yesterday. And today we are going to do series and parallel circuits. So we're going to finish that. We're not going to do it as a lab, but I have a couple of worksheets for you. And I'll show you what I mean as we go along. All right, so here we go. Let's get started. And we'll start with right here. Okay, so we were talking about this in class. Batteries. There are two ways of connecting batteries. Let's say I have more than one battery, and I can connect them in various ways, depending on what I want, okay? So you can connect batteries in series, or you can connect them in parallel. I guess I should underline that one too, in series or in parallel. Now, why would you do this? Well, let me show you a simulation. Okay, let's go back to the simulation here, and I will explain why we do something like this. Okay, so I'm just going to take this off. I had the circuit set up to show something else. I'm going to break the circuit here, and I'm going to actually take another battery and add it in. No, it's pointing the right way. Okay, make this wire a little shorter. Okay, so there. Now I have two batteries. Now I'm going to click on this battery, and I'm going to set its voltage to, I don't know, let's make it 20. And this battery is set at 25. Let's change it to 30, okay? So here's the deal. Why would I connect two batteries like this together, okay, in a circuit? Well, the answer is if I want more voltage in this case. So take a look. If I take my voltmeter and I measure across one of my batteries, I get 20 volts off across that one, and the other one I get 30, but when I go across both, I get 50 volts. So let's say my batteries, I have a set of batteries and I need more voltage. Well, I can connect them together in series to increase the voltage, right? So that's called, when you connect them in series to get more voltage, what you're doing is like increasing your energy per unit charge. But the limitation of the battery is like batteries can only give you so much current. So let's say these batteries, the most current they can give me is 2 amps, at most 2 amps, okay? So if I want 3 or 4 amps, then this won't help me get that, okay? So if my goal is to create a battery system that has a higher voltage, I connect them in series, okay? Now, the other way I can connect batteries is like this. Let's say I break this, and I break it again. Okay, so I'm going to do it, move this battery over, okay, and reconnect this wire here. Now I've got this other battery sitting here like this. So what I'm going to do with this battery is connect it to the circuit as well. I'll just join those up. Oh, I've short-circuited this battery. Okay, so just give me a second. Let me stop this. Okay, so let's cut it. I have a feeling this app does not allow me to do what I want to do here. Okay, so, it really shouldn't be doing that. Okay. All right, so this app does not allow me to connect batteries in parallel. So what you saw there is actually not correct. I should have checked this ahead of time. What the other battery will do would be to provide another source of current. Actually, let me make sure their voltages are the same. 30, here. They should have the same voltage when you connect them in parallel. Let me see if this works. I don't think it's going to work, but whatever, I'll try it. Oh, now it's working. Okay, there we go. Okay. All right, so I guess you need to have the same voltage, which there's a certain logic to that. Okay, so here, I've connected my batteries in parallel. Now what that does is this will not change the voltage. So if I check the voltage here across the one battery is 30, across my other battery is also 30, okay? So my circuit still gets a total voltage of 30 volts. But what the second battery does is it provides another source of current. So let's say, for example, like this circuit right now is drawing 1 amp of current from those loads that you see above, the 2 resistors and the 1 light bulb. But the deal is that the batteries will last longer like this. Okay, they'll last longer because each one is delivering about half of the current that they're getting, about half of an amp each. So if I were to take my current meter here and measure the current there, I'm getting about half of the current in that spot. And then over here in this spot, I should get around the other half, but I guess there's some resistance in the wire. That's why they're not exactly equal, right? They're both at 30 volts, yeah. So anyway, the batteries will last longer like this. Or if I need more current and one battery won't give me enough current, I connect them in parallel to get more current. Okay, so now with that in mind, let's go back to the notes. So connecting batteries in series, the goal of connecting batteries in series is to increase the voltage. So I get a higher voltage. That's a higher energy per unit charge. Now in this case, you can have batteries here. I have 2 batteries. I circle one in blue and one in red. The blue one has a voltage of 15 volts. The red one has a voltage of 25 volts. And when I measure across both of them with a meter, I get a reading of 40 volts with the voltmeter. Okay, so they add up, and that's it. Okay, so here, this voltage will equal V1 plus V2. Here, if this one's V1 and this one's V2, they add up together, okay, to give me more voltage. Now, connecting batteries in parallel is very different. It's a different reason for doing it. We're increasing the maximum amount of current you can get. And this has sort of a corollary effect. Batteries will last longer like this. When they're connected in parallel. Let's say you don't need more current, but you just want the batteries to last longer. We'll just put a second battery, okay, in parallel, and it will last longer. My Tesla would have lots of batteries connected in parallel, mostly because you want more current, okay? You want more current because to get the power that's needed to accelerate the Tesla at that tremendous acceleration that it has, you need as much current as you can possibly get running through that motor. And so there's lots of batteries connected in parallel inside the Tesla for that reason. Now, some are connected in series too. You can do both things. You can connect several batteries in series and then connect them in sets to a parallel circuit. And then you get more voltage and more current. And yeah, so you just get the desired voltage that you have, and then the maximum current will determine how much acceleration you can get out of the motor, let's say. Okay, all right, so now that we talked about batteries and why we connect them in series and parallel, let's talk about circuits. So this is now a new topic, a series circuit. So here I've drawn a series circuit for you, and as you can see, there is one path for the electrons, and this is the one path. I've highlighted it in yellow, okay? There are 3 loads on the path. There is first resistor, I call it R1. The light bulb, I'm calling R2. So a light bulb, any load can be considered a resistor. Okay, it's just that some loads have special symbols. So the light bulb is an example of that. And the third resistor, call it R3. Okay, so that is a letter R down there, R3. Now, the thing we know, what do we know about a series circuit? Well, since there's only one path, the current must be the same. This current, as the electricity flows through the circuit like this, sort of flowing around there, the current has to be the same everywhere in a series circuit. For proof, let's go back here. Let me get rid of this now. Okay, I'm going to delete that guy. I'm going to delete this, and I'm going to delete that. Okay, so here's a series circuit. Notice that everywhere I measure it, it's 1 amp. Okay, it's 1 amp. So it's 1 amp around the entire thing. So the current is the same everywhere, but the voltages could be different. Okay, like for example, the voltage across my first light here is 5. The voltage across the next resistor is 10, and the final resistor is 15 volts. Okay, so yeah, depending on your resistances, that'll determine how much voltage each one drops. Okay, I'm going to lower this to 25. I'll explain why later. That's an example that I have. All right, so what do we know about the currents then? So I'm going to circle this. We know that all the currents are the same. So I1, I2, I3, all the currents are equal, and we might as well just call them I. The voltages, though, we know that the voltage in the battery here, this is the battery's voltage, we know that has to equal the sum of the individual voltages in the series circuit. Okay, now we also know Ohm's law, which I just put in a box. V is equal to IR. So what I've done here in this next line is I've replaced V1 with I1 times R1, V2 I'm putting I2 times R2, and V3 is I3 times R3. And then I'm actually going to replace the battery with I times RT, and RT is the total resistance. Okay? And what I'm left with is what you see in this highlighted line here. Now, all the currents are the same, so they can be canceled out mathematically. And what you're left with is what I've already put a box around here, that the total resistance in a series circuit is the sum of the individual resistances. Okay? So that's probably not surprising to you. Like the total resistance is R1 plus R2 plus R3. So if I have like 3 5-ohm resistors, my total resistance would be 5 plus 5 plus 5. It's 15 ohms, right? So that's probably pretty logical to you. So moving on, it's not so logical with the parallel circuit. So let's talk about the parallel circuit. And it's the same scenario. I've got 3 devices, but this time I'm connecting them in parallel. And I'm connecting them in such a way so that there are 3 paths. Like here's one path here, and that has one load on it. There's another path, which I'll color here with a rainbow color. There's another path here, okay, that starts out from the power source as well. That's path number 2, let's call it, with the light bulb on it. And the only load on that path is the light bulb. And then finally, I'll use red, there is a third path through the third resistor, and that goes back to the power source like this. Each path has one load on it. Okay, so this is a parallel circuit. Similar situation as before, except they're not connected the same way. Now, here's the thing about a parallel circuit. We know that the voltages, okay, are all going to be equal. All the voltages here that you see, they're all going to be the same because remember the rule. Let's say the voltage was 10 volts. Well, if I take the blue path through resistor number 1, I have to lose those 10 volts because it's the only resistor on that path. If I take the rainbow path, which is the light bulb path, path number 2, I'll have to lose all 10 volts in the light bulb. Okay, and finally, if I take the red path, which is through the third resistor, okay, I'll have to drop the 10 volts there too. So all the voltages would be 10. The battery and each individual load would all have a voltage of 10 volts. The battery would be an increase of 10 and the resistor is a decrease of 10. So what do we know about the voltages? Well, I'm going to highlight it here. We know they're all the same. So we might as well just call them by one variable V for voltage. Okay, instead of saying 1, 2, and 3, and you know, V1, V2, V3, and voltage in the battery, might as well just admit the truth here. They all have the same voltage, so we'll just call it V. But the currents, on the other hand, could be different. Like, let's say, for example, I had 10 amps coming out of the battery. Well, I could get 1 amp here, 3 amps there, and 6 amps there for a total of 10. And they do not have to be the same, but they do have to add up to give me 10 volts, or 10 amps, I'm sorry. So let me highlight this for you with a rainbow. So the currents have to add up to give me whatever the current in the battery is. All right, now I'm doing a little math. The current in Ohm's law is given by V divided by R. So I'm going to take this equation that you see circled, and I already put an arrow down here. I'm going to replace all the currents with V over R. Now the battery will be replaced by the voltage in the battery divided by the total resistance in the circuit, because the battery sort of acts on the entire circuit, if you like. Okay, and then this is I1 here is this guy, I2 is that guy, and I3 is this guy. Okay, it's V3 over R3. Anyway, all the voltages cancel, but when they cancel, I'm left with a 1 on top of the fraction, and you get this equation here that you see in the box. Now, what I've just shown you is how total resistance works in a series circuit to start with, but also in a parallel circuit. And you can see in the parallel circuit, it's got this weird reciprocal, okay, relationship, the 1 over RT. Okay, we call it reciprocal when you take 1 over a number. But anyway, you know what? You don't need to know where these equations come from. I wanted to show you where they came from because I care. And I wanted you to see where they came from. But let's say you find it a little confusing, like, where do you get this? Don't worry about it. You do need to know how to use the equation though. Okay, and let's do an example. And I think the example will make everything clear. Okay, so here's an example. I'm going to take, these are great questions because they're kind of more realistic than the questions we've been doing. We're going to take a 5 ohm load, a 10 ohm load, and a 15 ohm load. So we have 3 loads. We're going to connect them to a 25 volt source. And my question for you is, what's going to happen? Okay. What voltage will each object get? What current will each object get? What's going to happen when you plug this in, okay, and it switches on? Well, let's do it. Step 1, okay, if we connect them in series, step 1, find the total resistance. So how do you find the total resistance? Well, you find it by, in a series circuit, you just add them straight up. 5 plus 10 plus 15. So there's 1 5 ohm, 1 10 ohm, 1 15 ohm, add them up. 30 ohms is the total resistance, okay? Now step 2, how much is the current? Well, to find the current, what we're going to do is we're going to take the total resistance that we just found. We're going to use Ohm's law that you see right here. And we're going to say, all right, so Ohm's law, the current will equal the total voltage divided by the total resistance. That's 25 in the battery divided by 30 ohms for the total circuit. And I get 0.833 amps, okay? Well, then I'm going to use my knowledge. I know that all of the currents in a series circuit have to be the same, and I know they're all 0.833. Okay, fair enough. So I know I1 is 0.833, I know I2 and I3. All the currents have to be the same because it's a series circuit, and they're all the same in a series circuit. Okay, so now that I know this, step 3, find all the missing voltages. So what is the voltage across the first resistor, the 5 ohm resistor? Well, I'm just going to use Ohm's law, which is what I put in the box right here. That's Ohm's law. okay, and just go V1 equals I1 times R1. Well, I already know that all the currents are 0.833. So now I just multiply it by R1, and I get 4.17 volts. So that's how much voltage will be in the first resistor. Well, now let's do the second resistor. I know that V2 is I2 times R2. Well, all my currents are 0.833, but R2 is 10. So that's going to give me 8.33 volts. Finally, let's go to our third resistor. Same equation again. So, but this resistor has a resistance of 15 ohms, and I get 12.5 volts. Now, if we've done our job correctly, these three numbers, 4.17 plus 8.33 plus 12.5, what do they give me? Okay, let's try it. And so I pull up my calculator, 4.17 plus 8.33 plus 12.5 equals, I get exactly 25 volts. Now, how much voltage was in our battery? 25 volts, okay? So you see it works. We got 25 volts. In other words, like all the math we did out works out beautifully, and we end up getting, we figured out what exactly is going to happen to these resistors, how much current they will get, how much voltage they will get if we plug it in. And these are very important questions if you're like someone who works with circuits to be able to answer, okay? All right, now let's do the same thing, okay? Except we're going to do it in the parallel circuit. Now, in a parallel circuit, we're going to connect the same devices, the same three devices plus the same battery together in a parallel circuit. But when you find the total resistance in step one, you have to use this equation, the reciprocal equation, because that's how it works in a parallel circuit. And remember, we did that up here. This is your parallel circuit resistance right here. So we have to use that form of the total resistance equation. I was telling the students in class, please don't treat this as an exercise in doing common denominator or fractions and stuff. There's a button on your calculator that will help you. Mine is 1 over x. It's this button right here. Okay, I'll show you in a moment. Yours could be something like this guy, but your calculator will have one of these two buttons. Okay, so here's how I would do it in my calculator. So let me put that there. In my calculator, I would take out the calculator and say, all right, and by the way, you'll see the button just, I can't point it to you because it's not going to work, but it's just above the equal sign, the 1 over x. So what I'm going to do is I'm going to press 5. First, I'll clear everything. 5, and then I go 1 over x, okay? Then I press plus 10, 1 over x. Then I go plus again, 15, 1 over x. And then I press equals, and I get 0.36666666. So I rounded that to, well, I showed you the number right here, but that's not equal to the total resistance. That's equal to 1 over the total resistance. So for me to find the total resistance, I have to take the reciprocal of that number. In other words, I have to do 1 over that one more time. So I take my calculator, I press my magic button one more time, and I get 2.73 ohms. So that's my answer right here, 2.73 ohms. Now, if you like, I have in this box here, I have shown you the order that you press the buttons on your calculator. Remember, you might be pressing x to the -1, this guy, okay, instead. Okay, so I press 5, 1 over x, then plus 10, 1 over x, plus 15, 1 over x equals. Then I press 1 over x one more time, and I don't have to press this one again. It just gives me the answer after that, but you may have to press it, okay? All right, now we found the total resistance, it's 2.73 ohms. Now let's take a look at the voltages and currents. Well, the parallel circuit, here's the good news. The parallel circuit, the voltages are easy because all the voltages are the same. So if the battery is 25 volts, that means your whole circuit, V1, V2, V3, they're all 25. Everything's 25. Now to find the current, I'm just going to use Ohm's law, V1 over I1. So for the first resistor, it's 25 over 5 is 5 amps. For the second resistor, 25 over 10 is 2.5 amps. And then finally, for the third one, 25 over 15 is 1.67 amps. Now, if I add them all up, I get 9.17 amps. But notice that if I take, this is kind of an interesting point, if I find the total current by dividing the battery's voltage by the total resistance, I get 25 divided by 2.73. That gives me just about the same exact number, 9.16. And if you've done your job right, it always works, okay? All right, so that's it. Like that's basically how we answer questions with series and parallel circuits. It's a bit tricky, I grant you, okay? Here, I just want to prove to you though that it does actually work. So here in this circuit, and this is bugging me, this meter, so let me get rid of this. Let me break that, break it here, and let me turn it around. So it's not upside down. All right. So here we have a series circuit. You can tell it's series, one after the other, there's only one path. I have set the battery to 25 volts. I have set the light bulb to 5 ohms, the first resistor to 10 ohms, and the last resistor to 15. So this is exactly the example that I gave you. Now, if you check the notes in OneNote there, in series, what do we get for the total current? Well, let's go back to it. So in the series circuit, what did we get? Well, we got, for the total current, right here, 0.833. Well, let's go back to our app. What do we get? 0.83 everywhere. So does it work? It absolutely does. Okay, so you can see that it's 0.83 everywhere. Now let's check the voltages. So first I will check my light bulb, which is the 5 ohm resistor. Oh, I've got my leads backwards. The 5 ohm resistor, I get 4.17 volts. You can see the number right there. So 4.17 volts. Okay. Now let's check the 10 ohm resistor. I get 8.33 volts. And finally, let's check the 15 ohm resistor. I get 12.5. Now, if you go back to our notes, it's exactly what we got. 4.17, 8.33, and 12.5. Genius, okay, works out perfect because we're doing everything right, okay? So everything worked perfectly and we figured it out. Now let's try the same thing in parallel. Okay, so to make the parallel circuit, I'm gonna break that. I'm gonna break this. Okay, I'm gonna break this too. Let's put the light bulb on the first path. Okay, and let's add a wire. We'll need a lot more wires for a parallel circuit, unfortunately. Okay, so that little light bulb is drawing a lot of current by itself. It's going to continue to do that. Let me break that too. Let me get another meter in here to measure current. And what I'll do is I'll put it right there. And then I will break this wire here. Put another wire here. All right, so now that's my 10 ohm resistor. Okay, now let's get some more wire. Finish this off. Let's put our meter over here to be consistent. Let's plug, okay, whatever, okay. And now I'll need another wire. Let's just go like this. Oh no, let's make it nice. So I'll put another wire like this. All right, so there's my parallel circuit. Now, if you remember in the parallel circuit, what do we get for the current through the 5 ohm resistor? Well, we got 5 amps. That's this. What do we get through the 10 ohm resistor? We got 2.5 amps. That's the second one. And what do we get for the 15 ohm resistor? We got 1.66666 rounded to 1.67 amps. Okay. Now, if you want to know what the total current is, it should be the sum of those things, 9.17. We got that too. Okay. That's the current coming out of the battery. Okay. Now, if I want to know the voltages, pay attention. I'm going to take my meter. All the voltages should be the same. So if I take my meter and go here, 25, right? Now, let me get rid of these lines. Okay, 25 volts here. Again, looking at this number, 25. And then finally, the last one, 25 also. And of course, the battery is 25. So it all works out. And we get, if you check one note, you'll see that we got all of these numbers. So basically, we figured out already, so you check our voltages, 5, 2.5, these are current values, and 1.67. 100% we got it right, okay? And we even got the total current right. It's good too. Okay, so basically what we did was, before we connected the circuit, we knew exactly what was going to happen. We knew how much voltage everybody would get, knew how much current they would all draw, okay, from the power source. So there's no mystery. We plugged it in, we knew ahead of time exactly what would happen, okay? So let's go to your homework. That's it for the lesson. I've got 2 sheets of questions for you. I think there's about 6 questions on each sheet. So let's just take a look. Your job here is to find all the missing values, and you're going to use Ohm's law. So Ohm's law, put it at the top. V equals IR. You're going to use that. And you're also going to use what you just learned about series and parallel circuits. So let's go ahead, okay, and look at this. They're all in series here, okay? And in series, it's pretty easy to answer the first question. So if you check this out, the question is saying, what is the total resistance? Okay, let's do that first. The total resistance here, this guy is 10 ohms, this guy is 20 ohms. In series, they just add up just straight. So it's going to be 10 plus 20, you know that is 30 ohms. So I'm going to write 30 ohms. Okay, that's 30 ohms for the total resistance. Now, what about the total current? Well, that's the current that flows out of the battery. Now, it's the same everywhere, okay, because there's only one path. But to get that, I have to divide. So my battery voltage is here, 90 volts. I'm going to go 90 using Ohm's law, okay? 90 divided by 30, which is the total resistance. Here, let me write that out for you. I'm going to do the battery's voltage divided by the total resistance, which is equal to 90 over 30, which is 3 amps. And they're all 3 amps because it's a series circuit. So all of my currents are 3. Now to find the missing voltages, I'm going to go I1 times R1. So I'm just going to multiply it out. R1 is 10, I1 is 3. So 10 times 3 is 30 volts. And for the other one, I'm going to go I2 times R2. Well, I2 is 3, R2 is 20. That gives me 60 volts in total. And my total voltage is 90 because 30 plus 60 equals 90, which is this guy up here. And it's got to work out that way. All right. So that's how you do it with a series circuit. No problem. Now, by the way, in some of these questions, like if you look here, in this question here, the second question right below it, they don't tell you what R2 is, but they do tell you that the voltage across R2, so this is V2, is 25 volts. Okay? Now, it's a little game you're playing with the numbers. I'll let you try to work that out. Please try to do it for tomorrow. Okay, so bring it in tomorrow, complete it so you can ask your questions. All right, there's another sheet that's parallel circuits. Okay, so here, the key difference is a parallel circuit. So it's a different formula that we use for the total resistance. But other than that, we're just using Ohm's law. Okay? All right, in parallel circuits, I like to do the voltage first. all the voltages are the same after all. So if you can figure out one of them, you've got them all. Since the voltage in the battery is 24 volts, that means all the voltages are 24 volts. Okay, so let's fill that in right away. The total resistance, they call it the equivalent resistance, is going to be, I'll do it in the margin. Here, I did it here for you. You go 1 over 12 plus 1 over 24. So again, I'll take out my calculator. I'll clear numbers out, and I'll write, okay, 12, 1 over x plus 24, 1 over x equals. Then I press 1 over x one more time, and I get 8. So RT will equal 8 ohms, okay, using that equation. So I get 8 ohms, okay. Now let's fill in the current values. Here for I1, I'm going to get V1 over R1. Well, V1 is 24, R1 is 12, 24 divided by 12 is 2 amps. Okay, now for I2, I'm going to get 24 over 24, so that's V2 over R2, that's 1 amp. So that means I've got 2 amps here, I've got 1 amp there, and therefore my total current must be 3 amps. Okay, so the total current is 3 amps, so that's 3 amps. I'll just write it down. But another way to get the total would be to say that the total current would be the voltage in the battery divided by the total resistance. Well, that would be 24 divided by 8 is 3 amps. So both ways give me the same answer. I get 3 amps no matter what. So you pick whichever way you like. That's it, guys. So try these other questions on your own. Please try to work it out. And you may need some help, not going to lie. But yeah, that's it for electricity after this. So congratulations, you finished it, if you can finish this part. All right, so that's it for me today. Guys, have a great day, and I will see you tomorrow. Don't forget tomorrow's costume day. I know Jacob has already picked out his costume, but for the rest of you, you know, whatever, maybe go with Jacob's theme there, and we can have like a, you know, like a Cinderella theme, basically. Okay, so if that works for you, Jacob, that works for everybody, I'm sure. All right, so have a good day, guys, and we'll see you tomorrow.